The next basic motion which we discuss is the free fall. The free fall is a downward vertical motion of bodies under the influence of gravity. Since the free-falling objects move along a vertical straight line, we talk about a one-dimensional motion, as in the case of the uniform linear motion. The only difference between them is that the free fall is not a uniform motion. The everyday experience seems to be in contrast to the statement that the free fall is always a downward vertical motion. By comparing the free fall of a ball and a feather, we will observe differences in their motion. If we drop them from the same height at the same time, then we see that the ball has a downward vertical motion, whereas the feather has a somewhat turbulent one, deviating from the straight vertical line. We can also notice that the feather falls much more slowly than the ball does, and the ball hits the ground earlier than the feather does. However, the significant difference between their motion is the consequence of the air resistance. If we carry out the same experiment in vacuum, then we can eliminate the effect of the resistance of the air. By putting the ball and the feather in a glass tube and sucking the air out of the tubes with a pump, we can drop the bodies in vacuum. As a result, both the trajectory and the speed will be the same for the falling ball and feather, and may reach the bottom of the tube at the same time. Thus we can conclude that there is no difference between the free fall of the ball and the feather in vacuum. The free fall experiment can be carried out a more systematic way, where the free fall of different objects can be observed and compared to each other. Perhaps the most famous experiment studying the law of free fall is attributed to Galileo Galilei, although there is no account by Galileo himself of it, and it may be regarded as a thought experiment. According to one of his pupils, Galileo performed an experiment on the Leaning Tower of Pisa, from which he dropped two spheres of different masses to demonstrate that they hit the ground at the same time, that is, their speed is independent of their mass. In such an experiment, we could use any object which is heavy enough to make the air resistance negligible during the free fall of the body. Nowadays, drop towers provide a facility for experiments measuring the law of the free fall or achieving a high quality of microgravity. Here we can see the Bremen drop tower, which is the main laboratory of ZARM. The tower has its drop capsule inside a drop tube under vacuum. During an experiment, a capsule is pulled to a height of 120 meters to the top of the tube and then released. After about 5 seconds the capsule lands safely in a deceleration chamber filled up flexible spheres. Under these conditions many measurements can be performed with a high precision. Such experiments can demonstrate that the motion of free-falling bodies is independent of the mass, the shape, the size, the material composition and other properties of the bodies. Then the law of free fall states that all objects fall with the same rate in a vacuum. This statement is in contrast with the long-standing view held by Aristotle, who claimed that heavier bodies fall faster than lighter ones do, based on such observations like the turbulent motion of the feather in the air. In his book Discourses, Galileo described a simple experiment with an inclined plane, so that he could make the observation of the moving bodies easier, and draw some conclusions on the law of free fall based on the results of his measurements. His basic assumption was that the motion with changing velocity follows the simplest form in nature. The velocity of the moving objects is changing with the equal amount in every equal time period. That is, the acceleration of a free-falling body is constant. Since any object falls fast enough to make the measurement of the covered distance and the duration difficult, Galileo wanted to decelerate the rapid motion by replacing a falling object with a ball rolling down a ramp. He designed a simple experimental setup with an inclined plane, as seen in the figure. The apparatus consisted of a wooden ramp with a groove cut into it and a bronze ball. When he let the ball roll down the groove he could track its motion started from different heights on the inclined plane, while measuring the time of the arrival of the rolling ball at the bottom of the ramp. The steps of the experiment were the following. Starting with the full length S of the plane, he rolled the ball several times down and measured the elapsed time and calculated the average time t. Then he rolled the ball down from a point so that the motion of the ball covered only a quarter of the full distance s, and measured the elapsed time. He found that its average was equal to the half of t. That is, if the ball travels for 2 times a given time, then it will cover 4 times the distance covered during that time. Galileo repeated the experiment by rolling the bronze ball on the plane with a higher inclination angle. When he used the full length s of the ramp, the average of the time during which the ball covered the distance s was t prime. If he reduced the covered distance to the quarter of s, the time average he measured was the half of t prime, as in the case of the ramp with the smaller inclination angle. As a result of the experiment, Galileo demonstrated that the distance which the rolling ball covers in a given time is always proportional to the square of the time. By increasing the inclination angle of the plane, he approached the condition for the free fall of the ball. Then he concluded that the relation measured between the covered distance and the elapsed time must hold in the case of free fall as the limiting case of the steeper and steeper inclination angles. The figure in the right-hand side illustrates this law. The free-falling ball covers 1 unit of the distance s during 1 unit of the time t. Then it covers 4 units of the distance s during 2 units of the time t. If the elapsed time is 3 units, then the ball covers the distance of 9 units. For the time equal to 4 units, the ball will reach the point at 16 units of the distance s, and so on. Let us see how Galileo formulated the theory of free fall. As we have seen, his basic assumption was that the free-falling bodies have a constant acceleration, that is, their velocity v is proportional to the elapsed time t, where the proportionality factor a is a constant. By virtue of this proportionality between the velocity and the time, the average velocity of the body for the time interval between the beginning of the free fall and a given time t is simply the half of the velocity v measured at the time t. That is, the average velocity is equal to the half of the acceleration a times the time t. The distance s covered by the falling body from the beginning of the free fall to the time t is given by the product of the average velocity and the time t. If we substitute the expression obtained for the average velocity into this equation, then we get half times the acceleration a times the square of the time t. Then we can see that the ratio of the distance s to the square of the time t is equal to the half of the acceleration, which is constant. This result corresponds to the findings of Galileo's inclined plane experiment. As we have already mentioned, Galileo needed to slow down the rapid motion of the free fall since no precise method was available for the time measurement in the Renaissance Italy. Galileo himself applied a water clock. He let water flow into a vessel while the bronze ball was rolling down on the ramp, and measured the weight of the amount of water gathered in the vessel. Nowadays, we can apply more precise methods to measure the relation between the distance and the time in the case of free fall. Here we have a sketch of a simple experimental setup with an electric mini-motor attached in a vertical position with its rotation axis to a stand. We can also see a cone-shaped plastic container filled with ink from which the liquid flows into an empty drum with a small hole on it. This apparatus is mounted on the axis of the motor. If we switch the motor on, it will rotate the drum filled with ink. Then the liquid starts to rotate together with the drum and the ink is sprinkled through the hole in the horizontal direction. We can apply a fixed shade with a hole to let the ink propagate only through the hole of the shade. As a result, we obtain a pulsating ink jet in a given direction with a repetition time depending on the operation frequency of the motor. We can adjust this frequency to obtain a given repetition time t of the pulsating jet. For example, let us apply a repetition time of 0.4 seconds. Now we can suspend a slat on a string attached to the stand in the front of the hole of the shade. If we start the motor and cut the string, then the slat falls down while the pulsating ink jet leaves stripes on it. As a result, we obtain a series of ink stripes on the slat and we can measure the distances between them and the first stripe, where the distances between the stripes depend on the repetition time of the ink jet and the velocity of the slat. Then we have a time series of measured distances which can be written in a table. Since the repetition time t of the ink jet can be set precisely by adjusting the electric motor, we only need to carefully measure the distances between the stripes so that we could minimize the measurement errors. The time ti is equal to I times the repetition time t of the ink jet, where the index I is an integer running from 1. Si denotes the distance of the I plus 1th stripe from the first one. Then the first row of the table will contain the elapsed time ti. That is t, 2 times t, ellipsis, I times t and so on. The second row of the table gives the measured distances si. That is s1, which is the distance between the first stripe and the second one. s2, which is the distance between the first stripe and the third one, and so on. In the last row of the table we compute the ratio of the distance si to the square of the time ti. That is, we have s1 over t1 squared, s2 over t2 squared, and so on. If we compute these ratios in the last row, then we will find that their values scatter around a constant, where the scattering is due to the measurement error. That is, the covered distance s of any point of the free-falling slat is proportional to the square of the duration time of the free fall, where c is the proportionality constant. If we want to determine the constant c, that is the ratio of the distance s to the time t squared, we need to choose relative large values for the distance, which mitigates the measurement error. We can use the ratios in the last few columns in the table calculated for the stripes far from the first one. Then the result of the measurement gives approximately 4.905 meter per second squared for the proportionality constant c. That is, the instantaneous velocity of the free-falling slat is equal to about 5 meters per second squared times the duration of the fall. This relation between the covered distance and the duration of the free fall was also demonstrated by Arthur Jules Morin, a French physicist, who constructed an apparatus to record the trajectory of a free-falling body as a graph. The principle of the free fall apparatus is illustrated in the figure. A falling body is guided by two parallel wires in the front of a large vertical cylinder, both of them installed on a frame. A sheet of paper is wrapped around a rotating cylinder, which is driven by a weight moving downwards on the opposite side. An air vane at the top of the frame also rotates with the cylinder and causes it to revolve at a constant angular velocity. An inked brush is attached to the body and marks its position on the sheet rotating with the cylinder. As a result, we obtain a diagonal trace of the falling body along the moving surface of the cylinder. The motion of the falling body can be analyzed if the sheet is removed from the cylinder and laid out flat. The vertical direction in the sheet corresponds to the instantaneous position of the body, whereas the length measured in the horizontal direction is proportional to the elapsed time. The curve drawn on it is one half of a parabola, which opens downward and can be interpreted as the graph of a distance covered by the falling body versus the duration of the free fall. Then the graph shows that the covered distance as a function of time is a parabola, that is, s is equal to the constant c times the square of the time t. The value of this constant is already determined in the previous experiment. We can substitute this relation into the definition of the velocity and write its magnitude, that is the speed, as the derivative of the distance s with respect to the time t. The derivative of the function c times t squared is equal to 2c times t. That is, the speed of the falling body is proportional to the time. Now, we can insert this result into the definition of the acceleration. The length of the acceleration vector is the derivative of the speed with respect to the time, that is the derivative of 2 times c times t. This gives 2 times c, which is constant, as we expected. Then we can conclude that the acceleration of any free-falling body is constant in time, and it is called gravitational acceleration. It is denoted by the letter g, and its value is 2 times c, that is 9.81 meters per second squared. Based on the results of the experiments presented here, we can now formulate the laws of motion for free fall. The distance s covered by a free-falling body in a time interval t is given by the half of the gravitational acceleration g times the square of the elapsed time t. This relation is illustrated in the figure in the right-hand side, which was already shown in the discussion of the inclined plane experiment. If the falling ball covers a unit distance during the unit time, it will cover 4 units of distance during 2 units of time. Then it will cover 9 units of distance during 3 units of time, and so on. The instantaneous velocity v of a free-falling body is directly proportional to the time t, where the proportionality constant is the gravitational acceleration g. That is, the acceleration of the free-falling body is constant and equal to 9.81 meters per second squared, which we call the gravitational acceleration g. We can also express the elapsed time of the free fall from the first formula. Then we obtain that the time t needed to cover the distance s by a free-falling body is given by the square root of the 2 times the distance s over the gravitational acceleration g. If we eliminate the time from this formula by applying the second equation for the velocity, we can determine the instantaneous velocity v of the free-falling body when it covered the distance s. Its value is equal to the square root of 2 times the gravitational acceleration g times the distance s. We note that all the experiments presented here demonstrated the laws of motion of the free fall only locally. If these experiments take place anywhere on Earth, then we will find these laws of motion remain valid. There is only one issue which has to be taken into account for precise numerical computations. The value of the gravitational acceleration depends on the latitude and the height above sea level. The variation of the gravitational acceleration is due to several effects, such as the shape and the rotation of the Earth, which we will study in dynamics. The gravity of Earth as a function of the latitude and the height is called the normal gravity. If we consider the measurements performed at sea level, its value is 9.78 meters per second squared at the equator, and 9.832 meters per second squared at the poles. In horizontal direction its value decreases by about 3 times 10 to the minus 6 meters per second square as long as the elevation is small against the Earth radius. Its average value is equal to 9.80665 meters per second squared. Besides the global variation of the gravitational acceleration, there are also gravity anomalies, which describe how much the actual gravity of Earth differs from the normal gravity due to the local geographic features of the Earth's surface, such as the presence of big land masses and ocean trenches. The normal gravity and the gravity anomalies were extensively measured throughout the planet, and many gravity anomaly maps are available providing a global coverage on the Earth's gravity field. Here, such a colorized anomaly map shows the local deviations of the acceleration, measured in millimeter per second squared. The unit centimeter per second squared is named after Galilei, and these maps normally use milli-Galilei. However, in many cases we can use a local approximation of the laws of motion for the free fall, where we assume that the vector g of the gravitational acceleration is constant. That is, the acceleration vector always points downward and its magnitude is constant, namely 9.81 meter per second squared.